Hey guys, so this video is for Unit 1, and Unit 1 is on the topic of functions, and it's going to be broken into 12 different lessons. Lesson 1 has the following objective. Your objective is to be able to identify whether or not a relation is a function. Now, when you have an objective like this, it's important to realize that you can't achieve your objective unless you know the meaning of the vocabulary and the words in the objective. So we might have to do a little bit of review, refreshing, backtracking, or explaining and teaching for some of you in order to achieve this goal for today. So some of the vocabulary we're going to focus on right now are the following words. We're going to deal with the word relation, domain, range, function, function rule, input, and output, among others, but those are the ones that sort of popped out to me as being main words to really go over throughout this particular lesson. So let's start off with a relation. So you might ask yourself, well, what is a relation? And you use this root word relation or relate or relationship in your everyday life. You use it in many classes, not just math class. So let's take a second and write out the definition of relation. Alright, so the definition we have here is a relation is a connection or relationship between sets of values. Now, I use the word connection. I don't really love the word or relationship to use that phrase, but I feel like it might be a better word to help people more clearly understand. However, I don't like to use the same root word in a definition. It's kind of silly. So connection is a good word to use, or relationship is the meaning we're looking for in this sense, between two sets of values. So you're going to talk about different sets all throughout math. A set could be the set of real numbers, the set of imaginary numbers, the set of natural numbers, whole numbers, rational numbers, or irrational numbers, the set of all even integers, the set of all positive numbers. So we're going to specify different sets. In math, the relation we deal with in our particular class is between x values and y values of ordered pairs. So get that definition down, and then we're going to continue. The next two words we're going to define right now are the words domain and range, and you might be slightly familiar with them. So we're going to write down these definitions now, and then we're going to have a little chat about them as well. So the definitions we have here are that the domain will be the set of all x values, and in parentheses, acceptable for a particular relationship. Now, why do we say acceptable for a particular relationship? Well, when we're dealing with a certain word problem, maybe we're talking about age of a person. If you're talking about age of a person, your domain is not going to be all real numbers. Okay? So, as an example, just to elaborate a little bit, if we were to find the domain when we're dealing with something like age, your domain would not be equal to, does not equal, the set of all real numbers. So this R right there is notation for the set of real numbers. The set of real numbers includes positives, negatives, zero, decimals, whole numbers, you name it. If it's not imaginary, it's real. So the domain can't equal all real numbers. When we're dealing with age, could your age be a decimal? Yes, that's actually fine. You could be 1.5, you could be 1.1 years old. So your age actually, when you really break it down, you could have decimals. But you won't have a negative age. So you might have to write your domain differently to qualify and to make sense for that word problem. So you might say something, maybe you'll use an inequality, all right? Inequalities are when you use something like a less than or a greater than. less than or equal to, greater than or equal to. So with an inequality, all right, so let's make this a little bullet down here. You're going to write something like age being A. I should probably say let A equal age in years. Your inequality A is greater than or equal to, I guess we could say or equal to the moment you're born, greater than or equal to 0. So with an inequality, that's how you might represent your domain. If it's a question saying, what's the domain in this particular word problem, and there's a word problem about someone's age, you might write a domain with an inequality like this. How do you represent that same domain with a number line? Usually we don't represent them with a number line. You might support it with a number line, or you might use the number line to get, really a little squished for space here, so with number line. Okay. If we were to use a number line for this domain, I know the green's a little hard to see, I apologize. Alright, if we're about to use there, you don't have to put every single tick mark you can think of on this number line. Really, most important thing is the main numbers that you're dealing with. So in this case, I have 0 right here. It's greater than or equal to, so I'm actually going to grab another color pen just so you could see it a little bit better. So this is where the age is 0. If we can equal 0, you may want to go ahead and color that point in. Now, which side of 0 are the numbers greater than 0? To the right. So you might show your domain in this way. You might support it with a number line. So your age is greater than or equal to 0. You won't have negatives. You can't say age is always positive because 0 is not positive or negative. You may support it with a number line. And now the third type of notation we're going to talk about at this moment is something called interval notation. So with interval, and I'm going to use capital letters for this because I think it is super important that we know how to do this. So with interval notation, and we're going to slowly practice this a little bit at a time. So I'm going to give you a little bit of a mini lesson on interval notation right now. So we're going to describe the interval that is our acceptable window here. So we're allowed to include 0 and anything greater than 0. So we go from left to right. If we start at 0 and it is included a closed circle, or greater than or equal to, or maybe the other way would be less than or equal to, but either way, if you're starting or finishing at a closed circle, okay, so you might want to write some notes down for yourself and draw arrows. When you do interval notation, for one thing, you're going from left to right, and a closed, I'm going to do this in blue so it kind of matches this right here. A closed circle will be represented by a square bracket. So that means I'm going to include the number right here. Now what number is that? That number is 0, comma, and after the comma, so you almost write it like an ordered pair where you have a starting point and a finishing point instead of an X and Y. So we start at 0, and now where do we finish? Well, in this case, it really shades that way, essentially forever. We're really going towards infinity. So I'm going to put positive infinity right there. Now 0, we can get to 0. It's colored in. That number is part of our domain, infinity. Infinity is more of a concept than a number. You can't actually reach it. Okay, we just strive for it. It's like striving for perfection. No one's perfect. So we're striving for infinity. You can't actually reach it. So when you cannot reach something and it's an open circle, we're going to use a parenthesis. Okay, so things that's your answer right there. I know it might seem weird if you've never seen anything like it. As we do more examples, you're going to get more comfortable with it. Okay, so just little clues about this. We're going to remember from, well, let's even write the word from over here, from left to right, which is a big place where people mess up when it's pointing and shading this way. Everybody wants to start here and go that way. Do not be that person, okay? Remember this moment right now. So you're going to go from left to right. Brackets represent closed brackets represent closed. You call them closed when they're colored in, okay? Like this, or it's equal to closed endpoints. So it could be a starting point, a finishing point, could be both. And we can also say parentheses represent open endpoints infinity and negative infinity. You don't put a positive with positive infinity, it's implied. Both require parentheses. They're considered open, okay, because you can't actually get there. And we'll elaborate on this more at another time, okay? So just a little bit of a mini lesson on interval notation. So now we know what a relation is. We'll get better at it, I promise. We had in our definition of a relation, we talk about the x values and the y values. So we need to elaborate on those. So we gave our definitions of domain and range. While we talked about our definition of domain and range, we talked about they have to be acceptable for a problem. We gave an example that age is a good example where not every number is acceptable. All real numbers is not acceptable. You're going to have to restrict your domain. So you're going to see that word and hear that word, you're restricting it. So it's like, all right, x values, you can hang out with any number except the negatives. I don't want you hanging around with those numbers. So you restrict it and you say that the a has to be greater than or equal to 0. Not allowed to be negative. We represented our interval, the answer to our domain. We represented it with an inequality. We represented it visually with a number line, which helped support us as we represented it with interval notation, which is going to carry on through pre-calculus, calculus, into college. So definitely important to know how to do that, okay? And like I said, we're going to keep practicing those. I'm going to kind of squeeze it in as a side lesson. Something we're going to just address quickly is the following. A function is always a relation, but a relation is not necessarily a function. So if you're in Algebra 2 and you took geometry last year, or maybe you're just familiar with geometry concepts, can you think of something from geometry that had a similar, no pun intended, relationship? Can you think of something from geometry that had a very similar relationship, and maybe it confused a lot of people, and maybe it was a big discussion for a class and people had to kind of go back and forth before it really clicked? Can anyone think of something? So this was supposed to be a student thinking. I don't know. He kind of, if you ask me, he kind of looks a little angry and mean. It's supposed to be more thinking. Yeah, that's a little bit better. I don't know. Sorry. Well, he was thinking and recalling his days in geometry, and this is what he came up with. He remembers the conversation about a square qualifies as a square and a rectangle, but a rectangle is only a rectangle. Okay, so a square is a more elite subset. It meets higher standards. It meets more requirements. That's why it can have a special label. So a function is a relation. It's a subset of the relations. So all functions are relations, but a relation is not necessarily a function. So what are we going to do from here? Well, we're going to need to define what a function is. Sorry, I felt weird without this little guy having a body. So let's go ahead and define a function now. So what we have here is the definition of a function that we're going to be working with. A function is a special relationship, and I'm actually going to go ahead and in the color I used for talking about relation, I'm going to be a little silly there. Special relationship where each input has a single, meaning one, output. It is often written as f of x. That's how you say it, f of x. This is not multiplication. It's a special notation. Maybe make that a little poem you say to yourself. It's not multiplication, it's special notation. There you go. Where x is the input and f of x is the output. So I forgot to close that. Here you see this diagram in a ton of textbooks. It's basically showing the function as a machine. You put in an x value, the machine does its work, and it spits out f of x, your output value. So there's your input goes in, you evaluate it in the machine, the function, and out you get your output value. Now, sometimes people, you'll hear them say, oh, f of x is really just y. Yeah, and no, it's more special. So that gets thrown around here and there. The nice thing about functions is when you have something like plugging in 2, you might think of this as what we call f of 2 equals 6. So your output value is really 6. 2 was your input value, but your final little statement tells you I plugged in 2 and I got out of it, I got a 6. Alright, so it's like I invested this much money and I really made this much money. So it's not like you just see the final product. You also have a little bit of a footnote telling you where you came from, where it all began. But now let's define a little bit more. We're going to talk about the definitions of input and output. So what we have written is input and output are terms that relate to functions. They are based on the rule of the function. So a little sidebar, an example of a function rule would be something like f of x equals 2x plus 1. Maybe you're given that and you're just practicing exercises involving a function rule. Maybe you read a word problem and you had to write your own function rule. Circumstances will vary. Input is the value of x that is applied to the function, and output is the f of x, the function of x, or the answer that is received as a result of putting x into the function. Now, when you apply a number to a function, you might feel more comfortable saying a phrase like you plug it into the function. So for example, let x equal 5. X equals 5. 5 is the input we're using. And x is a variable, so you can use different inputs. Your inputs will be selected from the domain. So you put in a certain x value. In this case, we're plugging in 5. Now, I intentionally, if you paid attention, I know, sorry, that's my dog making noise. Hold on. I wrote out the original function rule, f of x equals 2x plus 1. Now, everywhere you have an x, you erase it. You really don't have to write it first, but it's sort of like x marks the spot. But everywhere you have an x, you must treat them all the same. I erased the x, and where this one existed, there were no parentheses. So I put in my own parentheses to sort of mark off the exact location. And then I plopped in the input, okay? I put it in that function machine. I plugged in the 5. Now again, this is not multiplication, this is just function notation. Now here I did 2 times 5, which gave me 10, and then there's the plus 1, I just carried it over. There were originally equal signs here, that's why I can continue with equal signs. When you do the type of algebra where you're isolating a variable and solving for x, you can't just keep putting equal signs because it's not true. If you added something over and you subtract and blah blah blah, it's not still equal to what it was before. So that's why you should go vertically. Here I can go horizontal because Each step is equal to the next, and I get 11 as my output. So really, a final response could even be written as solely on the bottom as only f of x, or I'm sorry, f of 5 equals 11. And that's what I was talking about earlier as it being almost like a full, complete thought, a full sentence. When it's like saying when you plug in 5, you get 11. So you don't forget where that 11 came from. You remember because that 5 sort of acts like a footnote. Alright, so next we're going to look at 5 ways to view or represent functions, and really relations too. This is going to even be a side-by-side comparison, contrastation, if that's a word. Usually when you compare things, you're looking for what they have in common, and when you contrast them, you're looking for what makes them different. So it's really important that we address the similarities and differences so we can tell the difference between something that's just a plain old relation and something that is the more special function that we're going to focus on throughout this course. The first way we're going to look at as a way to view or represent functions and relations is a set of ordered pairs. Now, when you write something as a set of ordered pairs, the set is represented by these fun curly brackets, which a lot of people end up just making some crazy squiggles. So the set is enclosed inside of here, and it is a set of what? Well, it's a set of ordered pairs, so that's the thing that should be listed inside of here. If you were talking about a set of even numbers, well, then you're only going to have even numbers listed here. If you're talking about a set of students who attend school in New Jersey, well, this will be set notation and a list of student names who attend school in New Jersey. So it all depends on what comes after the word of right over here. If you have trouble making this squiggly bracket, I suggest you draw an S, and then without picking up your pen, I want you to draw a backwards S. Really, you should have a pencil. And then you draw the backwards S, and then the S a little bit. So if you could practice doing that, you should get better at writing the curly brackets for set notation. Now in purple over here, and blue over here, I've written 2 sets. One of them is a function, and one of them does not qualify as a function and should only be a relation. And we said we're going to compare and contrast. So let's look at what they have in common and what they have different. Now, this ordered pair is 1, 3, and this also has 1, 3. This one has 2, 3, 3, 7, 4, 7, 5, 11, 1, 3, 1, 4, 2, 5, 2, 6, 3, 7. Now maybe you have to flip back in your notes and you have to look again at the definition of a function. A function is a special relationship where each input we also said were the x values, has a single one output. Now this can get a little confusing. So if we look over here, here's an input. That input, 1, it's an x value. It corresponds with 3, the y value of 3, they go together, but it also goes with the y value of 4. That's 2, it goes with 5, but 2 also goes with 6. But each input, where are my inputs? So inputs earlier we did in green. So my inputs are underneath here. I have 1, 2, 3, 4, and 5. They're each used once. Nothing is repeated. But here, 1 is used twice. 2, it's also used twice. So this one is a function, okay? This one is a function, so you may be asked to determine whether or not something is a function, and this one here is not a function. And if you were to write down why it's not a function, you would say an input of 1 corresponds to the output of 3 as well as the output of 4, which is not allowed. The input of 2 corresponds with the output of 5 and 6, which is not allowed. Next we have a table. So in the table on the left, we have on the left column, we have the input, which is x. On the right column, we have output, which is going to be, in this case, represented by 2x minus 7. You might not have a clearly defined function rule like an algebraic expression like 2x minus 7, and that's okay. So that's not going to be what determines whether or not something is or is not a function. For the input, we ended up using 0, 1, 2, 3, and 4. For the outputs, we got -7, -5, -3, -1. And I left this part blank on purpose. So if we put in 4 as our input, we're using 4. What do we get out of it? Think about it. The answer is 1. 2 times 4 is 8, minus 7, 1. So this right here looks pretty good. I don't see anything wrong with it. I don't see why it wouldn't be a function. But before we do commit to that answer, let's look over here and see if we can maybe spot something that establishes a difference. Again, we have our input and output. I know I didn't write x or 2x minus 7 or anything like that, but like I said, that's okay. For the inputs, we're using 1, 3, 5, 7, and 7 again. Well, when you're dealing with any type of relation, there's no reason why you can't use a number more than once. For our outputs, we get 0, 4, 8, 12, and 16. So, if we had to decide from a table if something is a function or not, this right here will qualify as a function, and this one is not a function. And why is this not a function? This one is not a function because you have the input value of 7 going to 12 and then going to 16. So 7 is going to 2 output values rather than a single output value. Just like earlier, we had issues. We had the input value of 1, right? It went to 3 and it also went to 4. We had the input value of 2. It went to 5 and it also went to 6. So those are all reasons why something would not be a function. Let's check out the next way that we're going to represent our relations or functions. Here we have something called a mapping diagram, and this might be something new for you. So make sure you pay attention to little details here. Now you can use like an oval, you can use a weird little rectangle shape, it really doesn't matter, but really you need to sort of enclose and mark off all of your x values that are being implemented in your ordered pairs into the leftmost shape, and you're going to put all the appropriate y values in the rightmost shape. I try to always list my inputs and outputs in ascending order, meaning you start at the smallest and they're going to get bigger as you go down. So I go from least to greatest, even if the ordered pairs don't line up that way. Okay? That doesn't mean -2, 2 is an ordered pair. Maybe it's -2, 10, maybe it goes with -1, 4, something like that. Now, if an x value or a y value repeat themselves, unlike this table of values here, you're not going to list them more than once. You only write them down one time. And that's what makes a mapping diagram different visually than a table. Okay, it's one of the main components that makes it very different than a table. And then what you do is you sort of, we call it mapping, you map from an x value to a y value. You want to make sure that your arrow, you're going to use a line with one arrow, and your arrow is pointing at the y values, sort of like that little pipe machine that we went from here to there. You're kind of showing the path. So let's say that the ordered pair that you had was -2, 2. So in that case, I'm going to use red just so it stands out more. We draw an arrow from -2 to 2. Let's say another ordered pair you had in your set was -1, 2. Well, that'll go right there. 0, 4. All right, let's say we had 1, 10. That's okay. You go from 3, 8, and 2, 6. So those are all ordered pairs. Now for the next one. Let's say our first ordered pair was 1, A. And we're going to let A, B, C, and D, we're going to let those represent some constant values, okay? I don't know what they are right now. They're sort of like placeholders. So let's say one ordered pair was 1, comma A. Well, I would draw an arrow from the 1 to the A. Let's say another ordered pair is 2, comma D. Now, I couldn't put the letters in order because you don't know what they represent, so they're just sort of floating around like alphabet soup. Now, let's say we had the ordered pair 3, comma B, and we also had the ordered pair 3, comma C. Okay, so again, your arrows are only going to be on the right-hand side. What are we going to have to pay attention to? Well, sometimes your X or input value will split off and go to 2 different Y values, and other times you'll have a Y value that comes from 2 different X values. So which one of these causes something to be, well, really they're both relations. So which one of these circumstances causes something to not qualify as a function? And again, it's on the right-hand side, okay? So this right here is an X value, the X value of 3. 3 is being duplicated because 3 is going with B, and 3 is also going with C, okay? So that one right there, if you had to write a note there, or answer a question, it is not I don't know if I could squeeze it, but not a function, all right? This X value is going to more than one Y value, and that is right up in the definition. That's a big no-no. Let's check out the next way to represent relations and functions. As our fourth option to represent relations and or functions, we have a graph. So we have 2 graphs here. I have one on the left. This is actually a parabola. And then we have one on the right, and that is a circle. So think back to the definition of what makes something a function. Keep in mind these are both relations. They are relationships between inputs and outputs, between a domain and a range, between 2 variables, X and Y, the X and Y of an ordered pair. So these are all showing how they're related. That's fine, but which of these is a function? The definition of a function said that a function is a special relationship where each input can only go to one output. So where should you really be paying attention? So here's an input of 1. It gives me this answer right there. Input of 2 gives me that answer, which is 4, which is 1. This input of 3 gives me the output of 9. If I plug in any number, I will get out only one answer. However, here, if I plug in 1 for the X value, here's when X equals 1. Well, in this place, Y equals 0, but Y also equals -2, -4, -6, -8. So the X value of 1 has 2 output values that corresponds to it. That is a big, big no-no, okay? Is it okay for a relation? Sure. But can this possibly be a function? No, and that's what we're going to start our year focusing on in algebra. So a way that we test graphically, okay, how do we figure it out right away? A way that we test graphically whether or not something is a function is we look to see if it passes something we call the vertical line test. If you were to draw a vertical line through your graph and it would cross it more than once in any one place, then it's not a function. So this is not a function. I don't know if you could read that too well on top of the graph paper. Another thing that we can write is we can say fails the, and I'll make sure you spell vertical correctly, vertical, vertical, okay, like California. California is the long vertical state on the West Coast. Fails the vertical line test. Alright, this one is a function, we're good. Or, you know, it's not that you're not good if something's not a function, but this is a function, and this one is not a function because it fails the vertical line test. Vertical line test basically says the same thing the things in the earlier example said, that one X value is not allowed to go with more than one Y value. Our fifth and final way to represent a relation or a function we have an equation. Now this one is going to be a little bit more complicated than the others for figuring out whether it represents a function or not. If you have pretty good recall, then you should know that this is a quadratic equation. Y equals x to the second power, or y equals x squared. The equation is called a quadratic equation. This is the parent equation for all quadratics. And the graph of a quadratic is actually something called a parabola. And the parabola that it's actually representative of is this one right here, and it is a function. But you're not going to know what every single graph looks like. So what's some other way that we can maybe toy around with it? Now, for now, just for now, we'll evolve day by day. But for now, if you were to test out some numbers for x and for y, you want to make sure that when you put in a certain input, one input, that you get only one output from it. And if that isn't the case, then it's not a function. So our input are the x values. So let's say I'm going to let x equal 4, and I'm going to use 4 for both of these over here, so when I talk about that one. So I'll have y equals 4 squared. So I plug in 4, and now that means I have to square it. If I square 4, do I get just one single answer, or could I possibly get more than one answer? Well, 4 squared means 4 times itself, so that's 4 times 4. 4 times 4, what does that equal? There's only one answer. It equals 16. So far looks pretty good. We're getting an ordered pair, 4, 16. We plugged in an x, and we got one exclusive y value. Alright, looks pretty good. Now, what about over here? Again, I'm going to let x is still our input. Just because things look different doesn't mean that y is the input. So let x equal, let's use 4 again. That means I have 4 equals y squared. So I need to solve for the y value. You need to use an inverse operation. How do you get rid of the fact that this is being squared? Well, how do you undo addition? You subtract. How do you undo multiplication? You divide. How do you undo a square? You take a square root. Now, when you're the one who took a square root, the square root symbol was not written on your equation to begin with. When you're the one to take a square root yourself of a constant, of a nice positive constant over here, it's very important that you find both answers. Now, what do I mean by both answers? When you multiply something by itself and get a positive answer, you could have multiplied a positive number by itself and gotten positive 16. We also could have multiplied a negative number by itself, negative 4. What if my input was negative 4 instead? I would have negative 4 squared, which is still 16. So negative 4 also goes with 16. Is that okay? I have two different x values going to the same y value. That is okay. That looks like the horizontal line test. That, which would be up here, sorry. Alright, where you have two different x values, both going to the same y value. That also looks like this situation right over here, where a y value is being used multiple times, but it came from two different x values, so that is okay. Alright? So these look fine. So when I take the square root of y squared, that leaves me with just y equals, what times itself is 4? 2. What else? Negative 2. So positive and negative 2. What does that tell us about our ordered pairs? That means I have the ordered pair 4, 2, because remember you do x, y, but I also have the ordered pair 4, negative 2. So now I have the same x value, 4, corresponding to two different, instead of one single y value, two different y values. So this is not a function. We're going to elaborate much more a little rule of thumb is when y is being squared, that usually leads to some funny business. Some inevitable square root with a plus minus, multiple responses. So to err on the side of caution, if you have a y squared somewhere in the problem, if you're not sure, I might just go ahead and say it's not a function. This one over here, y is not being squared. If y is only being raised to odd powers, again, you're probably in the clear. It's probably a function.